Good afternoon, or almost afternoon, everybody. Next Thursday, next week, we'll hear from Professor Kulkarni, San Francisco State University, and the topic will be how to tame these enormous, gigantic text searches. You would think text searches are a given, but it turns out that there are lots of kinks there. Anyway, that's next week. Today I have this great pleasure of introducing you to Landon Curt Noll, who, when he was a teenager, discovered or co-discovered the largest possible primes, Mersenne primes at a time. And he's going to reveal the secret to us as to how you can discover your own super large primes. So let's welcome our speaker.
Thank you very much. Again, I'm Landon Curt Noll. I'm a resident astronomer at Cisco. And a number of things I do at Cisco, one of them is to use computers to investigate. That is, computers not as an end of themselves, but as a tool to investigate. And one of the things we can do investigations are on what's called computational number theory. It's quite appropriate for me to give this talk at in the Cal State University system. As a young kid growing up on a farm, I had the opportunity to take classes at what was then Cal State Hayward, now I guess Cal State East Bay. And I used basically money that I got selling eggs, and they were really great champion eggs, to basically buy my classes. So at that time it was about $35 a unit. You can show up a little box, and I was audacious enough to just go up to the university and say, hey, here's money, I want to take classes. And you didn't have to do essays or any of that sort of stuff, you could just attend. And so I was given the opportunity and then given access to some machines which Seymour Cray had designed that were sort of large, basically at that time fairly substantial machines by control data that was used by the Cal State campus system to find large primes. So it's quite appropriate that I'm here today. And we actually went around to a number of the data centers or computer centers in the Cal State University system, and we've spent a number of times. We came up here to Sonoma State to use the machines up here as well. So I'm going to talk about the grand coding challenge of finding a new largest known prime. This is actually going to be selected slides from a large tutorial. This PDF down here is something you can go and visit to get the main tutorial. It's a sort of a half day lecture, but I'm going to give you sort of the highlights of this for a limited amount of time. So prime number we define as a natural number, 1, 2, 3, 4, 5, that sort of thing. That's prime if and only if it has two distinct natural number divisors. That is one in itself. And by the way, 1 is not prime. For details, ask me afterwards. The largest known prime right now is this monster here, 2 to the power minus 1. It would take about 4,400 pages to print out the decimals. Using the system that Conway and I developed on naming a number of any size in the English language, you start off with large numbers like this. You'd have about 74 reams of paper just to print the name of this. So it's a pretty big prime. The nice thing is there's no largest known prime. So whoever has the record, you can break it. You can find a larger prime. Now, you'll hear a lot about Mersenne primes. And this French monk, very interesting fellow, started talking about when 2 to the power minus 1 was prime. He claimed that when these numbers, when you raise 2 to these number minus 1, you got a prime. He didn't say why. Turned out he was wrong in a couple of cases. But after 300 years of his name, of Mersenne, Mersenne was the name of the monk associated with these numbers, 2 to a power minus 1 is called a Mersenne number. Now, in looking for primes, I mean, there's the true way to do it is just say, well, you just start looking for 1, 2, 3, 4, 5 and looking for divisors. And if you fail to find all but 1 in itself, it's prime. That's really impractical for numbers of any reasonable size, even industrial size primes, or it's too big to happen. If you look at all the methods that are developed around factoring, breaking a number down to its set of primes, and the methods around primality tests, they only sort of intersect in the most degenerate trivial case, that is exhaustive search. Most of the time, when you do large primality testing, you say, this is a property that only prime numbers have. This number has this property, therefore it's prime. You don't go through the process of factoring in order to try to prove it anything of any particular size. Now, primality testing, at least in the age of little computers, got started in the mid-1950s. A number of theorists found ways to get time on the biggest machines, or the only machines around at that time, and started producing fairly record primes of that size. Particularly this group here, Robinson and Lamer, had a pretty good string of stuff, and it was based upon tests developed by Lukaw that Dr. Lamer extended in his thesis work. I had the privilege of studying under him at the University of California, Berkeley. Remarkable man. It's the most efficient primality proof known in terms of it gives you a definitive, it's prime or it's not for Mersenne numbers. And its theoretical argument suggests it's actually maybe the most efficient test possible in terms of size. Basically it says 2 to a power minus 1 is prime if and only if this thing u sub p is 0 mod that. Well, what we're saying here is that 0, if you divide u sub p by the number you're testing and you get 0 as a remainder, then it's prime. So the way you do it is you say we define u sub 2 as 4, and you calculate this recursion of the previous number squared minus 2 mod the number you're testing, get the remainder. So what you have to do is start with 4, square the previous term, subtract 2, divide by the number you're testing, get the remainder. Do this a number of times. If when you get to u sub p, if it's 0, it's prime, otherwise it's not. So let's take, for example of is 2 to the 5th minus 1 prime? Well, it is, but let's prove it. So u sub 2 is 4 by definition. So u sub 3 is going to be 4 squared minus 2, which is, what's 4 squared minus 2?
14.
14? Okay, 14 divided by 31 leaves a remainder of 14. So 14 squared minus 2 is 194. So 194 mod 31, give you, it happens to be 8. So 8 squared minus 2 is 62. Divided by 31 leaves a remainder of 0. Therefore, it is prime. In the case of 2 to the 11th, you do this thing, you get something which is not 0 at the end, and so you know it's not prime. So that works for 2 to the power minus 1. So I had a privilege with when I was at a young lad, and basically taking time away from the large cyber machine, Cyber 174 machine that was used throughout all the California University campus, was idle about 23 and a half hours a day. And so I used about 6,000 hours of time per year in developing this particular test. And so it was in, I think it was October 78, and then February 79, we cranked out 2 primality proofs. And even today, it's one of my license plates I have of the Mercian. It's there. But records are made to be broken. And in particular, what we did was we laid out all of our methods, gave out all of our source code, gave out all of our factor tables, sort of like the open source of mathematics at the time. And these, Slovinsky and Nelson, using our factoring tables, using our trick for doing the mod fast, used a Cray 1, bigger machine at the time, and found a number of other primes. So, but the problem is you run into something called the exponential wall. What do I mean by that? Well, think about what you have to do this test. You have to p-1 times, square a number, subtract 2, divide, get the remainder. And the numbers you're dealing with are between 0 and the number. So you're dealing with, if it's a large number you're testing, you have to square it, subtract 2, divide by the number, get the remainder, and do that for p times. And so you think about what's the effort involved? Well, if you square, the old pencil and paper method, if you have a 3-digit number by a 3-digit number, as you're doing, let's say, a generic multiply, you end up with 9 products. You didn't carry in out your terms, but squaring is roughly a number of digits squared operation. Subtract 2 is trivial. You just subtract 2, and occasionally you have to borrow, but it's a pretty fast operation. Turns out you can do the mod to the p minus 1 very fast by a shift and an add. If this is your binary number, you peel off the bottom p bits, you're doing mod to the p minus 1, add the two pieces together, and that's your result. If it turns out to be greater than 2p minus 1, you carry, you just add it over, split again, and that's basically done in linear time. So, and here's an example again. If you do this number, you just split off the bottom 31 bits, add them together, you get a carry, you throw that around on the side, and that's the end. So the mod is actually pretty trivial. It's just a shift and an add. So to compute use of x, you've got a square, that's all p squared operations. There's rack 2, which is fairly instantaneous. A shift, the mod is a shift and add and p operation. So what ends up dominating your time is a square. And you have to do it p times, so the primarily test goes up by the cube of the power, which is kind of unfortunate. If you think about, let's say it takes you to do 1 day to test m sub p. You double that exponent, it'll take you 8 days. 5 times exponent will take you 4 months. 10 times exponent will take you 2.7 years. You run into this exponential wall, even for the biggest machines. Well, one of the things you can do to kind of cut down the work is you can pre-screen your tests. It's consuming to do the Lucas-Lambert test for big machines, even though it's the most efficient probability test we know. But if you can find a trivial factor of the number, then you can avoid testing it. So you're not trying to factor it in order to tell us if it's prime, but say if I can find a small factor, then I don't have to bother with the primality test. And so there are rules about Mercian kind of special form that the factors have to be. You can go in and do some searching, screening. Typically, you can emulate about half of your candidates. You can find small factors of where small is in relative, is sort of relative, but you can find small relatives factors of it. So it comes down to, factoring can limit half of them, but it comes to how fast can you square, because the subtract 2 and the mod are fairly trivial. So how fast can you square? That's an interesting thing, and that's one of the things we were doing on the Cyber 174 was to look at how squaring very efficiently, and it got down to having to code stuff in assembly, getting the actual timing books of the CDC machine, and all the construction counting to do various magic to try to eke out every cycle you can in that inner loop of the square. But there are tricks you can do to square faster. For example, if you're actually squaring and not multiplying, you notice that half of the time you're repeating a result. A 6 times 4 is the same as 4 times 6. So you can eliminate half of the work if you're doing that way with just squares. It's not bad. Probably a better thing to do is use a different base. There I'm showing you base 10, which is nice for people, but computers like to do bases and powers of 2, particularly powers of 2 where it's the word size. So you have a 64-bit machine, and you can multiply two 64-bit numbers to get a 120-bit result. Divide a 120-bit number by a 64-bit number to get a mod remainder. You can add two 64-bit numbers together or subtract. You can do stuff in base 2 to the 64th. So you have fewer digits, your square is not so bad. But it turns out that's, again, you're just kind of pushing the exponent wall a little bit farther down the path. You still run into this significant exponential wall no matter how big your machine is. So the trick that we developed in 1990, a thing called Ondel 6, was to square by using transforms. And there's this thing called the convolution theorem that states that ordinary product is the same as the dot product of the transforms. And well, what does that mean? Well, dot products are really nice because that cross product is all those digits by all those digits. That's your digit squared operation. Dot product is merely just taking an array and multiplying pairwise all the values. So the way you multiply is you transform the two numbers, do a dot product, which is just a linear pairwise multiply, and then inverse, and you've got them. You got something that can be used as a product. So in the end, to do this thing again and to square a number, you've got to transform the number, dot product itself, basically square all the terms, and inverse transform. And that's pretty good because, again, that if it took you 1 day to test 2 to the p minus 1, it'll take you 2.7 days rather than 8 days to do twice the exponent. 40 days instead of 4 months to do 5 times the exponent, 7.6 months instead of 2.7 years to do 10 times the exponent. So now what you've done is that wall, that exponential wall you run into is a little bit more gradual in its slope. Now you might say, what do you mean transform integer? If you know about things like Fourier transform, the spectral analysis, and we're dealing with integers, well, what's this craziness going on? Well, best way to think of it is think of the integer as you develop a wave, right? Let's say talk about in binary. You've got this wave, and that's your waveform. And Fourier transforms work on infinite repeating values. You just take that number and infinite repeat, and you ask, what are the harmonics in this bit pattern? And you'll get some spectral thing sort of looking like that. You then square those harmonics, square the frequencies, and inverse transform, and you've got your result. Now, the problem is the Fourier series, so forth, an infinite sum. And last I heard, infinite sums are really long, take a long time to do, even in fast computers. So what you have to do is you end up, however, going along in a term to say, I'm getting a term that are so small that I don't need to worry about it, and you sort of cut off the end of the infinite sum. And but that gives you some errors. But if you end up where your terms are actually really truly trivial, then your errors won't quantize. They won't turn into individual integers, and you're okay. Another thing you have to do is deal with things called Nyquist frequency stuff. And again, I have to point out, you know, as a kid, I was really interested in number theory and integers, and really the hardcore, what they call fundamental number theory. And all this real analysis and all that other stuff was not so interesting. It turned out, in fact, the curse of my thing was I didn't pay much attention, and I had to go and pay a great deal of attention to things like real analysis and frequency stuff to get this thing going well. So anyway, one thing you have to do with transforms is you have to pad it. Typically, what you're doing is, one thing is that when you square the number, you're going to get something twice as big. So you need to be able to hold that value. You're also dealing with frequencies that are much higher than the top of the number. The square is going to have much higher frequencies involved. So you essentially typically have to double the thing by padding with zeros. So what you end up needing to do is say, all right, to square a number, I'm going to take my p-bit number, pad it with zeros, so I'm under Nyquist frequency. I'll transform the points, and then oftentimes when transforms, the libraries and methods require you to transform a certain size, right? There's transforms that say, well, I can transform a power of 2 points. So you have to pick a power of 2 that's greater than double the size and pad again. But with the padding, you perform the transform the padded value. You square each individual point. Again, it's a dot product just going down the line. You inverse transform, and then typically you have to what's called normalize, where you, let's say, divide by the number of points to sort of normalize the value. And then you have to propagate the carries. It's fairly simple to do with a straightforward, Fourier transform. You have an FFT library like the nice GNU FFT library out there. You basically put your digits. Fourier transforms work in complex numbers, so you just make the imaginary parts 0 and the real parts be your digits. So you load your digits into the array. You perform the transform. You square each individual point. You form the inverse transform, and you do the normalizing, which is divided by the number of points. And then basically you get something that you can propagate the carries, and it works. So if, for example, in this particular case of 32, we're going to square 32, so we pad it with extra digits. We get these complex numbers. We do the Fourier transform. We square each complex value. We round an inverse transform. We round to integers, extract the reals, right? So we're basically rounding there, extract the real values. And then we get these values here as if we didn't do any carries. But here's a 12, so you carry the one over here, that case 10, carry the 1, and basically get your 1024. It really does work, and the math works. And it actually does pretty well. Now the details are in the rounding. Again, you're not doing infinite sums. You have to chop off the end. And if you chop off too soon, then you're going to get errors involved, and that errors are going to propagate, quantize, and become part of an integer, and then you're off. Because again, with these tests, you have to do it correctly. You have to do it down to every bit correct on the integer. So you typically find that you have to do a lot less precision than your floating point can give you For example, in the Omdo 1200 where we did this, we had a 96 bits on our mantissa, and we found that base 2 to the 23rd gave us enough wiggle room where all the sines and cosines and so forth could be done correctly. So you have to analyze your rounding errors. It's also good to put around that transform a sort of checking value. Like you can check the number, kind of like a 9 sort of check to make sure that your square doesn't, or not, or at least to try to catch cases where your transform will give you a bad value because you, let's say, had an energy spike or something in it that you didn't count for. Now, Fourier transforms work, but there's some non-Fourier transforms where the convolution theorem still holds. They're especially good, integer transform is pretty good on some CPUs where the integer math might be faster than the floating point. We, on Number 6, use something called a PFA fast Fourier transforms in Winograd's radix FFTs. It's sort of a thing where we did the transform mod a bunch of primes and used Chinese remainder theorem to get the result on the other side. But GEMS uses a transform, integer transform developed by the late Dr. Crandall of Reed College. And you can also roll your own efficient transform. I would ask your friendly computational number theorist or mathematician for advice. But you can certainly roll your own transforms with the architecture you use. So there are Fourier transform-like things out on the net. There's examples of shown like a Strassen algorithm that the GNU multi-precision mathematical library uses. It does a pretty good job. Fourier's algorithm is also something out here which also has a pretty good number theoretic transform. And there's a pretty good primer on this sort of thing. So these transforms, which square faster, help you push the thing along. And again, we have to do, you start with a number of Mersenne prime candidates. And by the way, in the case of Mersenne prime, 2 to a non-prime minus 1 is never prime. So you start with a bunch of 2 to the primes where p is prime. You look for small factors, limit about half of those cases. And then you, for each individual test, you start with 4, square them on 2, using the basically padding, transform, square, inverse transform, divide real parts, propagate the carry, subtract 2, mod by shift and add, and if you end up at 0, you have a party, and if not, you try again. This is how you do it. And to encourage that, a very generous donor to the Electronic Frontier Foundation produced something. We developed an award called the Cooperative Computing Award, and by the way, I'm one of the judges of the Cooperative Computing Award. So one of the things I did is made myself ineligible. That's why I'm not going after chasing these numbers. But there's real cash prizes. We've awarded a $50,000, $100,000 prize in 2009, but unclaimed $150,000 for the first prime number with at least 100 million decimal digits. Now, leading zeros don't count. If you look at their rules, we're onto that sort of thing. But it's unclaimed as of today. And the $250,000 prize for the first one with a billion decimal digits in size, first primality proof. You just can't sit there and say this is prime. You actually have to, there's official rules, and one of the rules, I designed the rules, and one of the rules, particularly I made it sure it was rule 4F, for those who know about military stuff. You must publish your proof in a refereed academic journal. So before you even talk to us, publish it in a refereed peer-reviewed journal. And so you basically have to give us an abstract of and a citation of the publication. There's some of the rules involved, but the publishing is actually a trivial part, although I know that reviewers sometimes are cranky too, but the computation is really the effort if you can find it. But, and here's one of the things I want to say, while the Mercian test of the Lucas-Lehmer test for Mersenne number, 2 to the power minus 1, is the most efficient we know, it's not the best way to find a new largest known prime. Why? Well, Mersenne primes are rare. I mean, it's only 42 out of the first 25 million Mersenne numbers are prime. If you look at the Mersenne, the 3 million Mersenne numbers that are between 1 and 10 million digits, there are only 7 of those who are prime. They're getting very, very rare. And in order to test large and large, you're having to climb that exponential wall. It gets pretty bad. Another thing that's happening is that even though the machines are, quote, faster, the numbers you're dealing with and the size you're dealing with bust your cache, are bigger than your typical cache systems there. So you end up becoming memory bus limited. And while they can get more and more gigahertz on a core, that typically doesn't do you much good if your memory, the bus to your memory sort of sucks rocks. So you have to deal with that. Another thing is mean time to error. The machines today, I think, typically have a much worse mean time to error than some of the machines of old. I mean, for example, we did a study on the Intel Nehalem processor and found that a well cared for processor would make a calculation mistake about once every 30 weeks on average. 30 weeks, 2 plus 2 is 5, right? And this Mersenne test requires you to do it exactly. Any bits, any flaws, the calculation is garbage. So now you're dealing with stuff where, if it took, the largest known prime test was 31 days by GIMPs. When you deal with 100 million digits or more, you're dealing with things that are much bigger than your mean time to error of your processor. So you've got to do some deals with the error stuff. So the Mersenne chase is fine if you want to do it for GIMPs, but if you want to find a new largest known prime, because there's plenty of non-Mersennes primes out there to look for, you need to do something else. So I'm going to talk about this Reitzel test. What's a Reitzel test? Well, we're going to search for numbers h times 2 to the n minus 1. So instead of 2 to the power minus 1, it's a multiple of a power of 2 minus 1. Now, there are a couple of advantages with this test. The Reitzel test is kind of Lucas-Flamer-like. It's only about 5 to 10% slower, if you will, for that than the typical Lucas when you're rolling along in your loops. And when h is small, particularly when h is small but not too small, the distribution of primes h times 2 to the minus 1 is about the same as the regular primes. These Mersenne primes, 2 to the power minus 1, are rare. But h times 2 to the minus 1, when h is not something like 1, 2, or 3, it's a relatively big number, they're just like J-random primes. Another thing is all that Lucas-Flamer type test depend upon the exponent. As n grows, you hit the exponential wall based upon n. Well, what you can do is pick an n, fix it, and change the h. So 5 times 2 to the n minus 1 and 7 times 2 to the n minus 1 take roughly the same amount of time. So you can optimize for an n, that n may be just bigger than the largest known prime, and look at multiples of 2 to the n minus 1 and do that test. Another really good thing about this is because these numbers, this sort of harmonic, you have sort of a arithmetic sequence of these numbers is distributed like the primes, you can eliminate lots of candidates. In fact, you can typically eliminate better than 96% of your candidates just by sitting on small trivial numbers. What you find, however, is you don't want h to be too small. If h is 1, then you're the Mersennes and you're stuck with stuff. And even 3 times 2 to the n minus 1, they're somewhat rare. So you need h to be reasonably large. A good rule of thumb we use is that h has to be less than 2 to the n. That's easy because 2 to the n is big. But you typically use h bigger than about twice the exponent. And they appear to be about as prime as your typical primes there. So you can guesstimate the amount of effort you need to find a largest known prime. There is, while we suspect there's an infinite number of Mersenne primes, there's no guarantee. They might have found the largest Mersenne prime, which would make searching for the next one rather hard. So a lot of advantages for this. But how do you do it? And it's relatively easy to do that. We at the time, the largest known prime was the exponent was 216091, and so we picked a number whose exponent just a little bit bigger, and we had this multiple of that. We found it to be prime. We did test a number of those things, but as Dr. Schenk said, it was just a fart larger than the largest known prime. Basically, you go up there, and if someone finds a larger prime, you crank your n up and start going what we call going sideways, not up the exponential wall, but go sideways out the side. And so we did that successfully in 1990. I was a member of the what's called the Omdal 6 team, and we used at that time also transforms to do our multiplications faster. So what is this test? Well, the Reisel test is very much Lucas-Lehmer-like. You say that, but a couple of things. N doesn't have to be prime anymore. So h on 2 to the minus 1 is prime if and only if h is less than 2 to the n, and this thing u sub n is 0 mod the number you're testing. Now it turns out that u sub 2 is not 4. U sub 2 is this function called v sub h I'll talk about in a moment. But you're basically taking the previous term, squaring it, subtract 2, mod the number you're testing, getting the remainder. You do that all the way up to u sub n, where n is your exponent. And if you get 0, you go party, and if not, you try again. There are some good examples of this Reisel test. We wrote a tool, David Bell and I, known as D-Bell, wrote this tool called Calc. And it's a C-like multi-precision interpreter where it computes based upon rationals or complex rationals for stuff. It's really good for algorithm development. And so we wrote our Lucas-Lehmer, the Reisel test that the Amdahl 6 group used. We wrote it sort of in Calc. We didn't use Calc to run the machine, but the description of the algorithm is found in that nice file. And source code contains lots and lots of comments. There are actually more comments than their code, as a good code should have. But, and we have lots of references to papers, and we don't just cite something in Knuth. We say this Knuth, this paragraph, this version, this spot, to show you what we're doing. So, let's talk about this test. Well, unlike the Lucas-Lehmer where you say u sub 2 is 4, you have to compute u sub 2. And this u sub 2 is this function called v. Now, when h, that's your multiplier, is not a multiple of 3, you start off with v sub 1 is 4, you do this recursion to compute v sub h being your multiplier. So instead of u sub 2 is 4, u sub 2 is this v sub h, which is this recursion set. Now when h is a multiple of 3, it gets more cranky. You've got to have to deal with things of quantic residues and Jacobi symbols and other stuff, and it goes on and on. There's another sort of stuff. It's actually a fairly involved thing when to find u sub 2 when h is a multiple of 3. Now, fortunately, 2/3 of the numbers are not multiples of 3, so that's pretty good. You can just decide to avoid that. Another thing you can do is use this thing in Calc, lucas.cal, where we actually show you how to do all the stuff for computing when it's a multiple of 3. Actually, we cheat. We can actually find about 99.9% of the time when h is a multiple of 3. And those other 0.1% are too hard, and you can sort of ignore them. But one of the ways to do that is you could use Calc to actually generate your u sub 2's if you want to ahead of time. So let's take a test, example stuff. Let's test 7 times 2 to the 5th minus 1 using the Reisel test. So it's prime if only if 7 is less than 2 to the 5th, which is true. And this thing called u sub 5 is 0 mod the number we're testing. So the first thing you have to do is start off with u sub 2. And because 7 is not a multiple of 3, we do this nice recursion. So we take 2 and we go through this thing to produce v sub 7, which is 138. So we have to do a little bit of work to start off with u sub 2, but not too bad. And then once we have the 138, we just do this thing of square minus 2 mod, square minus 2 mod, square minus 2 mod. By the way, there are other values you can use for u sub 2. Calc does a side thing. 49 also works as well. That recursion will work, but there's actually faster ways you can do tricks, again, to get it even faster. But essentially, only difference is we start off with a different value than 2. We're modding by something that's not 2 to the power minus 1. And we see whether they get 0 at the end or not. Not so bad. Now that modding. Remember, when we modded using the Mercennes, on Mercennes, we just did a shift and add. To do a shift and add mod h times 2 to the minus 1, you have to play a little bit more trick games. You still split it into 2 pieces, but you take j divided by your multiplier, rounded down, and j modded by your multiplier shifted by n bits, and k. You add those 3 terms together. If they exceed, you go again. But it comes down to essentially a little bit more than shift add. It's a shift divide. And one of the reasons why you want to keep h to be small, but not too small, is you want this division to be a nice single integer division. You don't need some multi-precision h thing. So if you keep h well within the size of the word, this j, this piece divided by h is easy to do, and j mod h is also trivial to do. Shift it up, add it together, and it works. So the mod, you don't have to do all the division is really awful to do. It's awful to do in digital. It's awful to do in floating point. So you can avoid the division, do so, and this is the easy way to do that. So again, you want to keep h small, but not too small. Again, h is 1. You're back to the Mercennes, and they're rare. So you want to keep h small. If you have a 64-bit number, you can want to keep h less than 2 to the 63rd, so you don't have sign problems. But as long as h is sort of bigger than twice your exponent, you're into the sort of you're into the typical thing. So maybe h between twice your exponent and 32 times your exponent is a good range to look at. Now, you can pre-screen as well. You don't have the nice properties of restricting what a factor of 2 to the n minus 1 is, but you have some really good things about the sieve. There's this thing called sieve. Aristophanes, really smart Greek that came up with this method of finding primes, where you say, well, you ignore 1 and start with 2, you knock out every second value. Then you take the next one, not there, not knocked out 3, and knocked every third value. 5, knocked every fifth value, and so forth. You go to the point where the number is the square of the number is exceeds the end of your table, and the rest are primes. Now, it's not good for finding primes, but it's good for finding factors of numbers. What do I mean by that? Well, there's some tricks you do with a sieve. I mean, one of the things you can do is there's no point in actually having even numbers in your table. So you can eliminate the even numbers. And in fact, you don't even have to have things consecutive odds. You can do an arithmetic sequence. Particularly this arithmetic sequence of saying, I'm going to take the numbers h on 2 to the n minus 1. So here, 1 times 2 to the fifth minus 1, 2 times 2 to the fifth minus 1, up to, in this case, 7 times 2 to the fifth minus 1. You have this arithmetic sequence. And what you do is you start with, let's say, the number 3, because we're not interested in, they're not even, so we don't have to bother with that. We take the first prime 3, find the first number divisible by 3, and then every third number will be a multiple of 3. So once you find the number, first value in your table, that's a multiple of a small factor, then you eliminate every nth value. Here's basically a vector thing where when you find that first number, you can then go to every nth bit and just turn them all off. Right? So if you have this large table of h candidates, remember you're fixing n, and it's bigger than the largest known, bigger than the 2 to the n minus 1 for the largest known prime. When you fix n, you have a whole bunch of h's, and again, you wouldn't use h as 1, you'd use h starting at some higher number. And you start with 3, you find the first one divisible by 3, you can do it by something called a trick called a multiplicative inverse. Once you find that number, then every third value, you've now eliminated a third of your candidates in one swoop. 5 and 7. Now it slows down a little bit. And one of the questions is, well, how much do you sieve? There's one pragmatic answer to say, well, you should sieve. One says if it's faster to eliminate numbers by sieving than by testing, sieve. But on the other hand, by sieving, you'll never find the largest known prime. So you need to test some numbers, but at the beginning, you want to do a heavy sieving. And so one of the things you can do is you can look at the rate at which you're knocking out bits, right? So rather than simply turning off bits in a vector, you might want to test to have a counter saying, when I take a 1, it might be prime, to a 0, it's definitely not prime. I record the rate at which I'm knocking out bits. And you might find at the beginning, after a couple of months of sieving, you're still knocking out sieves at the rate of dozens per minute. It probably is a good idea to do mostly sieving and do a few testing. Again, you have to test something, because if you don't test, you won't find a prime. But it's sort of there's a strategy involved in that you can consider. So again, what do you do to find the largest known prime? Well, you pick an n, where 2 to the minus 1 is bigger than the largest known prime. Pick an h, let's say somewhere between twice n and 32n. You look for small factors by sieving. You limit about 90% of the candidates. And while you're doing that, you begin to code and test this particular thing, which is going to be the Reisel test, which is computing v sub h, which is your u sub 2, doing the square minus 2 mod, and you're going to do that by transforming square h point, inverse transform, normalize around as needed, propagate your carry, subtract 2, do the slightly more complicated shift and add thing, do the mod. You do that a bunch of times, and if you end up with 0 at the end, you got a prime, and if not, you keep trying. So that's pretty good. I mean, now what we have is a test where we can go sideways. We can avoid the exponential wall the Mersenne people are going. We can use the best methods for for multiplying fast. But there turns out if you're hardware enabled, or you have some friends in hardware that can do some stuff, it turns out there's some pretty nifty circuit designs you can do to multiply and add much faster than classical computers can today. There's a particular device where you have a bunch of parallel state machines that can do a multiply and add in linear time, not n log n or n squared, but linear time. This particular device has each module has 11 bits of state, so it's a pretty small thing. The inputs come in on the beginning value, and they have a chain of all these things. Linear it's a linear, so you don't have this cross product, cross bar thing. It's just a nice linear line of these state machines. And it does the multiply and add at the same time. So that, remember that square subtract 2, you can do that actually at the same point. Although subtract 2 is easy, but it's a nice thing to think about. The other remarkable thing is that at time t, at clock t, you're inputting the input values, the teeth bits of your input. And at clock t minus 1, the teeth bit of your output comes back. You have all this thing that's propagating down. So it takes n cycles to load in your n bits, and it takes 2 n cycles to get all your answers back. Right? So at clock 3, when you're inputting the 3rd bit of your input, you're receiving the 2nd bit of your output already. It's a pretty remarkable set of stuff. And again, these are chained together. The chain is doesn't take much in terms of there. You receive 1 bit from the right, 3 bits from the left, and copy over 2 bits from the left. So it's not a huge bus system. You need n over 3 of these devices, but it actually works fairly well. All these devices are relatively the same. There's some circuit optimizations you can do. The actual calculations that need to do are pretty simple. Most of the time you're doing this particular operation. And this AND is a Boolean AND. These are single bits. So you're taking a bunch of single bit ANDs and you're doing up to a 7-bit add. Right? That's a fairly simple circuit that you can design. The gates are not very long. And so again, it's a very, very simple circuit in that 11-bit state machine. And that nice 11-bit state machine is your memory is local. You're not going over a bus. Everything has its own little set. So you say, well, you can certainly run this state machine at 100 gigahertz. I mean, the depth of this logic of doing this operation is pretty small, only a couple of gates. So 100 gigahertz is not pushing the technology very fast. But if you did a 100 gigahertz thing, you'd need about you can multiply 22 million digit numbers in only 1.5 milliseconds. So it took the 774 hours to test the largest known prime. At 100 gigahertz, you're running at 24 times faster. And remember, you're doing it linear time. Even the Reisel test people have a slightly steeper exponential thing, but you can really zip along pretty well. It's a very embarrassing parallel circuit that I think a class who does stuff on ASIC design is very simple ASIC. You can string these things out and do, I think, some amazing stuff by a little bit of software and hardware interplay. So I want to mention some final words of encouragement. The results, the record, goes to the first person to calculate correctly. Not necessarily the fastest, but the first person to do it correct. And Dr. Langer drove in mind that a slow, correct answer is infinitely preferable to a fast, incorrect answer. If you're going to be generating wrong answers, you can do it very, very fast. So slow, correct. Compute smarter. You do not have to be the fastest machine to do this. I never used the fastest machine to get a record prime or record twin there. I always computed smarter. My records were done by machines that were not the fastest. Another thing is don't optimize prematurely. Premature optimization is the bane of correctly running program. Get the program to work correctly first, and then optimize and build lots of tests. You're going to have to build, you have to do QA on steroids. The code that I did for the cyber was ended up being a stack of punch cards about yay long, but it took me about 2 years to debug and make sure it was absolutely positively correct. You have to also so start the code running and then improve. Another thing is you've got to test. Again, machines today are not reliable. You've got to catch the hardware errors, the software errors, the assembler errors, I mean all kinds of memory management errors. Don't trust the system, don't trust the memory management. Double check everything. Have checks along in parallel to make sure what's happening is reasonably correct. It's not uncommon to say that you might spend most of your cycles will spent testing. Maybe somewhere, typically about only a quarter of your time will be spent testing a new candidate. Internal checking and so forth, check and recheck and recheck. Besides, when you test a number and it comes out to be prime, you better do it again, just to make sure on a different machine. And then, of course, you've got to get somebody else to confirm your result, because we're doing science. So they've got to basically, you've got to have the time to do at least 3 tests. But again, it's sort of worth noting that nothing is 100% error-free. To say, well, how to know it's correct? Well, if you've done all these checks, your source code is open to inspection. That means when you publish, you better have decent source code. Don't submit this blob of fancy Python with all these word symbols. Comment the hell out of it and show your method and show that it actually works, right? Because you're going to get rewarded when someone can verify your result and your result passes peer review inspection. So start from the beginning by coding in a decent manner. That's fairly obvious for someone to see. Again, to find a number, you'll probably end up having to do lots of tests. But I go through the analysis of how many tests you might do. You can estimate the number of tests that it does. You probably will do somewhere around 100 million, basically about 4 million Reitzel numbers if you pick a number, like h times 2 of that minus 1, bigger than the largest known prime, h being between here and here, between twice and 32 times the exponent. But you end up doing about 4 million of those tests. But if you're in hardware, you can crank out the stuff and do it in parallel, or software, you can do it in lots of parallel and lots of PCs, but lots of checking because PCs are really bad at doing correct numbers. When we took the Helm results to Intel, we showed them saying, hey, these machines are pretty bad. Intel's response, and I kid you not, was 30 weeks is longer than the mean time of error of Windows. And therefore, we don't care, right? Intel is not at selling you computers that work. They sell computers that are efficient, that work good enough, right? But in case of this computational number theory, it has to be perfect. So you have to do lots of checking and expect to spend much more of your time in QAing and error checking and rechecking than in doing checking. Still, could someone or a team in here find a new largest known prime? Absolutely. You have the capability of doing this. You have access to machine and resources. They're particularly you focus on the correctness of coding. You don't have time to rerun. Make sure your code works. Start it going and continue to improve it. Focus on error correction detection. Compute harder rather than just smarter. Have a team where you use different strengths involved in doing this team project. Dr. Lamer said happiness is just around the corner. Problem is, we have a multi-sided polygon building, but happiness is just around the corner. Don't get discouraged. Keep going, work in a team, use complementary strengths for stuff. Write your own code. I mean, yes, there are samples of GNU code out there or other things you can do, but you're probably better off eventually writing your own code and tuning it yourself. But you can reuse obvious stuff there. But again, if you write your own code, at least understand if you use someone else's code, how it works. Again, could one of you do this or a team of you do this? Absolutely. It's actually, I think this takes a little bit of effort. It's not quite a plumb at waist height. You have to go up the ladder a couple of steps, but there certainly are plumbs out to get there. You can, again, dethrone the Mercennes. So, thank you.
We have time for one question and one answer.
Yes, sir.
If you develop a custom hardware solution for calculating these primes, how would that get verified, or how would that checking process work?
So the question is, if you develop custom hardware, how would you check it? Answer is that you probably would want to have the time where someone else goes and uses a completely independent system, perhaps a software system, to check your primality. I mean, the advantage is you have a high confidence, this number appears to be prime based on the Reisel test. Please perform this calculation. And they take that H and N, they can do it even in a fairly straightforward way. It might take them a month or so, but they'll be able to hopefully confirm your result. One more question? Maybe someone else here has a question. Otherwise, I can give you a question.
Okay.
All right. Again, look at this URL at the bottom. This is a big, half-day tutorial with all lots of other examples. I skipped over lots of details of things for time, but give this URL a check out.